Hello everybody. So today we are going to take the chemical bonding. I am taking the topic chemical bonding, in which I am going to discuss the trigonal bipyramidal geometry. So this trigonal bipyramidal geometry is observed when the central atom is having 5 electron pairs with it, according to Vesper theory, and the hybridization must be sp3d. And this geometry, we generally consider it as an asymmetric geometry because we have two types of hybridizations in this. So sp3d, it is formed with sp2 hybrid orbitals and pd hybrid orbitals. So sp2 hybrid orbitals, they take up the equatorial position in the geometry. They take up the equatorial position, and pd hybridized orbitals, they take up the apical or axial positions. And due to this difference in the nature of hybridization, generally the apical or axial bond lengths are longer than the equatorial bond lengths. So in terms of bond lengths, it is asymmetric, and in terms of hybridization, it is asymmetric. And if you observe the bond angles in the geometry, between any two equatorial positions, it is 120 degrees. Between an equatorial and apical position, 90 degrees. And between apical positions, it is 180 degrees. So in this geometry, where should we place the lone pairs or multiple bonds or electronegative atoms? This is the geometry where we are expecting number of questions from various universities. So the position of lone pairs, multiple bonds, electronegative atoms. We can explain based on Bent's rules. So the first one, lone pairs. Lone pairs generally occupy the hybrid orbitals where the percentage S character is more. Why the S character must be more? When the S character is more, the orbital can easily penetrate towards the nucleus and can get sterilized. So in trigonal bipyramidal geometry, S character is more in the equatorial position. So lone pairs occupy equatorial positions. Multiple bonds that generally include double or triple bonds. They prefer the sigma bonds, which are formed with more S character in the hybrid orbital. Multiple bonds prefer the sigma bonds formed with more S character in the hybrid orbital, because this more S character, it can decrease the bond length and it can increase the covalency. So in trigonal bipyramidal geometry, these multiple bonds, they generally occupy equatorial positions. Now more electronegative atoms. More electronegative atoms, they have to withdraw more electron density towards themselves. Therefore, they prefer the hybrid orbitals with less S character. So, in the case of trigonal bipyramidal geometry, more electronegative atoms occupy the apical positions where S character is almost negligible. Now, the distortions in trigonal bipyramidal geometry. Distortions. Distortion is generally observed due to the presence of lone pairs. So, in the trigonal bipyramidal geometry, if all the electron pairs are bonded pairs, it is trigonal bipyramid. And if there are one lone pair, if there is one lone pair, it is distorted tetrahedron or seesaw structure. Two lone pairs in the geometry, structure would be T-shaped. Three lone pairs in the geometry, structure would be linear. So what is the difference between geometry and structure? Geometry includes all the bonded pairs and lone pairs. Structure includes only bonded pairs. Because of lone pairs, we observe the distortion in the geometry. Now, when we go through the examples, First one, PCl5. Phosphorus is the central atom. So now it is undergoing sp3d hybridization, where we have 5 bonded pairs and 0 lone pairs. So the geometry or structure, it will be trigonal bipyramid. And the chlorines, they are occupying both the equatorial and apical positions, trigonal bipyramid. Now PCl3F2. Phosphorus is the central atom. So we have 3 sigma bonds with chlorine, 2 sigma bonds with fluorine. On the whole, 5 bonded pairs, 0 lone pairs. Geometry or structure is trigonal bipyramid. But how does this molecule differ from PCl5? That is, it is having 2 fluorine atoms which are more electronegative. So according to Bend's rule, these fluorine atoms, they occupy the apical positions as they are more electronegative. And the third one, XeO2F2. So in this we have 4 bonded pairs, 1 lone pair. So hybridization is sp3d, geometry trigonal bipyramid, but the structure is distorted tetrahedron due to the presence of 1 lone pair. And here we have 2 double bonded oxygens and 1 lone pair. So what are their positions in the geometry? According to the Bend's rule, multiple bonds or lone pair, they'll occupy the equatorial positions. So the structure of the molecule is distorted tetrahedron or. So the next example, ICl3. Iodine is the 7th group element. So we have 3 sigma bonds with chlorines and 2 lone pairs. So it is 3 bonded pairs, 2 lone pairs, hybridization sp3d, geometry trigonal bipyramid, structure is T-shape. So according to Bend's rule, these 2 lone pairs, they'll occupy the equatorial position. Equatorial position, so when we ignore this lone pairs, molecule appears to be T-shape. Geometry, it includes all the bonded pairs and lone pairs, but the structure includes only the bonded pairs. Now, XeF2. So xenon is the central atom, 2 fluorines, that is 2 sigma bonds with fluorines, and we have 3 lone pairs. So 2 bonded pairs plus 3 lone pairs. Hybridization sp3d, geometry trigonal bipyramid, but the structure is linear because of the lone pairs. And according to Bend's rule, all these 3 lone pairs, they are going to occupy the equatorial positions. So the molecule appears to be linear. When we ignore the lone pairs, molecule appears to be linear. Okay, na? So now let us see what are the different questions that are being asked in the previous years based on this trigonal bipyramidal geometry. So the first question is, why all the bond lengths in PCl5 are similar and why it is ionized in the solid state? So this is asked in the IISc Bangalore. So let us see the questions that have been asked in the previous years based on this trigonal bipyramidal geometry. So the first question which was asked in IISc Bangalore, it is, why all the bond lengths in PCl5 are similar and why it is ionized in the solid state? Already we have discussed that the axial bond lengths are longer than equatorial bond lengths. If that is the case, in PCl5 all the bond lengths must not be similar. But in this molecule, in trigonal bipyramidal geometry, we have the resonance. So what is that resonance? That is the continuous exchange of positions of equatorial and apical bonds. The equatorial and apical bonds continuously exchange their positions. And this type of resonance, we generally call it as Berry pseudo rotation. Berry pseudo rotation, or we often call it as pseudo-Berry rotation. Pseudo-Berry rotation, and because of this pseudo-Berry rotation, the apical and equatorial bonds continuously exchange their position. So the difference between apical and equatorial bonds is lost, so all the bond lengths become similar. And this resonance or this rotation is absent in the solid state because of the rigidity of bonds in solid state. In solid state, bonds become more rigid. So this rotation of, that is exchange of apical and equatorial bonds is not possible. Therefore, PCl5, in order to stabilize itself, it undergoes ionization in the solid state. PCl4 plus and PCl6 minus. Now the second question, number of resonance structures in PCl3F2 and what is the most stable structure? It is also the question which was asked in ISC Bangalore. So here, what are the resonance structures? The only thing is we have to exchange the apical bonds to the equatorial bonds. So we have two fluorines in the apical positions. So in first resonance structure, one of the apical fluorine, it is exchanged to the equatorial position, and in the third structure, both the fluorines, they have come to the equatorial position. So these are the three resonance structures possible for PCl3F2. And among these three, which is the most stable structure? Obviously, it is PCl3F2. Because when we apply the Benz rule, it says that more electronegative atoms must be in apical position. And based on this molecule, there was one question. So what is the bond angle between fluorine atoms in PCl3F2? What is the bond angle between fluorine atoms? Since they occupy the apical positions, the bond angle between fluorine atoms must be approximately 180 degrees. Now, the next question is position of oxygen atoms in HgO2F2 and approximate bond angle between them. So this was the question asked in TIFR. So what are the positions? So this is the structure of HgO2F2, and according to Benz rule, both the oxygen atoms, double bonded, occupy the equatorial positions. Lone pair also occupies equatorial position. And in the equatorial position, bond angle will be approximately 120 degrees. So the oxygen atoms occupy equatorial positions with approximate bond angle of 120 degrees. Now, the geometry and structure of SF4, and this is the most important molecule which was asked in several universities. They asked the structure or geometry. So sulfur is the sixth group element, 4 bonded pairs plus 1 lone pair. Hybridization is sp3d. Geometry, trigonal bipyramid. Structure, seesaw. Because the lone pair, it is occupying the equatorial position, so the structure is either distorted tetrahedron or seesaw. And the next one, the geometry around iodine in I3 minus, triiodide ion, I3 minus, structure of I3 minus, total number of lone pairs in I3 minus, and the angle between iodine atoms in I3 minus. So these are questions which are being asked in CSR and also in the Kerala set, one of the Kerala set exam. So now, first of all, what is the hybridization in I3 minus? So iodine, it is 7th group. We take 7 electrons. So 2 bonded pairs and 3 lone pairs. 2 bonded pairs, 3 lone pairs. So one of the negative charge on the molecule, it is being taken as an extra electron with the central atom iodine. So we get 2 bonded pairs, 3 lone pairs. So it is 2 bonded pairs plus 3 lone pairs, sp3d. Geometry, it is trigonal bipyramid. Structure, it is linear. Now let us see the answers for the questions. First one, geometry around iodine I3 minus. It is trigonal bipyramid. Structure of I3 minus, it is linear because of lone pairs. Now, angle between iodines in I3 minus. So both the iodines, they occupy the apical positions. So the bond angle is 180 degrees. And total number of lone pairs in I3 minus. So how we are going to take the lone pairs? Central atom, because of the negative charge, it gets an extra electron. So on the whole, it will have 3 lone pairs. And each iodine is the 7th group element. So it should have 7 electrons. Out of 7 electrons, 1 electron is used in bonding. The remaining 6 electrons form 3 lone pairs. So similar is the case with the other iodine. Out of 7 electrons, 1 electron is used in bonding. The remaining 6, they become 3 lone pairs. So in this, you are asked with total number of lone pairs in I3 minus. Means we should include the lone pairs of both the central atom as well as the surrounding atoms. So the total number of lone pairs in the molecule, it is total number of lone pairs equal to 9. And if they ask you the total number of lone pairs around the central atom, there are only 3. Around the central atom only 3, but in the whole molecule, it will be 9. Next, number of lone pairs, bonded pairs, structure of ClF3. So chlorine, it is the 7th group element. So we take 7 electrons. So it is 3 bonded pairs plus 2 lone pairs. Hybridization is sp3d. Geometry, it is trigonal bipyramid. Geometry, trigonal bipyramid. Structure, it is T-shape. And what are the questions here? First one, number of lone pairs. So number of lone pairs, they didn't ask you the number of lone pairs in the whole molecule. They are not asking the number of lone pairs in ClF3 molecule. So they just asked number of lone pairs. So we have to consider the lone pairs around the central atom. So the number of lone pairs around the central atom, 2. Now number of bonded pairs. You have 3 bonds with fluorine. So the number of bonded pairs are 3. And the structure of ClF3, it is T-shape.